If you watch the construction of a cable-stayed bridge from a distance, the sequence of events appears to violate basic construction logic. The tower rises from its foundation in the conventional way. Concrete is poured in successive lifts, climbing formwork ascends the shaft, and the tower grows upward day by day. But then something unexpected happens. Before the tower reaches its full height, workers begin attaching stay cables to the upper portion of the shaft and connecting the opposite ends of those cables to deck segments that are being cantilevered outward from the tower base, segments that are hanging in mid-air, supported by nothing except the cables attached above them, and the counterbalancing weight of segments going out on the other side. The deck is not built from the ground up. It is not assembled on temporary falsework and then lifted into place. It grows outward from the tower, suspended in space, in both directions simultaneously, with each new segment added at the tip, and immediately connected to a new cable anchored higher up the tower. By the time the deck segments from adjacent towers meet at midspan, the bridge deck has been constructed almost entirely while hanging from cables, attached to towers that were themselves still being completed. The sequence looks like the deck is being built before the structure that supports it is finished. In a precise engineering sense, that is exactly what is happening. And understanding why this method is possible reveals the fundamental principle of cable-stayed engineering. The confusion comes from applying the intuition of conventional construction: build the supports first, then place the supported structure, to a structural system where the supports and the supported structure are mutually dependent from the first moment of erection. In a cable-stayed bridge, the tower is not a freestanding column that carries the deck as a separate operation. It is one element of a self-equilibrating structural system in which the cables, the deck, and the tower all work together to carry load through a specific combination of tension in the cables, compression in the deck, and bending in the tower. Remove any one element from that system and the others cannot stand in their intended configuration. The construction sequence must therefore build all three elements simultaneously in a sequence that maintains structural equilibrium at every stage, including stages where the bridge looks nothing like its finished form and where the load paths are different from the completed structure. To understand the scale, consider the Russky Bridge in Vladivostok, Russia, currently the longest cable-stayed span in the world, at 104 meters between towers. Each tower rises 321 meters above sea level. The main span carries a 6-lane highway across the eastern Bosphorus Strait. The stay cables, 168 per tower, range from 135 to 580 meters in length and contain up to 91 individual high-strength steel strands each. The deck is a composite steel and concrete structure approximately 36 meters wide. The total weight of the deck between the two towers is approximately 23,000 metric tons, entirely supported by the cable system during construction and in service. At this scale, the forces in the stay cables during construction can reach tens of thousands of kilonewtons, and the compression force in the deck introduced by the cables can reach hundreds of thousands of kilonewtons. Managing these forces throughout the construction sequence, adjusting cable tensions as new segments are added, compensating for concrete creep and shrinkage, and correcting for thermal expansion and contraction, is a continuous structural engineering operation that runs from the first cable installation to the final deck closure. Most people, when they observe the balanced cantilever construction method, assume that the two arms are always in perfect balance. That assumption is correct for the target geometry, but not for the construction reality. The deck segments on each side of the tower are added sequentially one at a time, and at any given moment the two arms may be at different stages of completion. One side may have one more segment, or the concrete on one side may not yet have reached its full design strength. Each of these asymmetries creates a temporary out-of-balance moment at the tower base that the tower must carry in bending. The tower design must accommodate the worst-case temporary imbalance that can occur during the construction sequence. This temporary bending moment is often larger than any bending moment the tower will experience in service. Because in service, the deck is a continuous structure that distributes load. But during construction, each cable force is an independent load. The balanced cantilever sequence begins after the tower is raised to anchor the first set of stay cables, the lowest group. The first deck segments are short and heavy, placed close to the tower base where the cable angles are shallow. Here, cable forces are highest relative to the vertical component that actually supports the deck weight. As the cantilever extends and cable anchor points move higher up the tower, the cables become steeper. Steeper cables carry more of the deck weight directly and introduce less axial compression into the deck. This is why cable-stayed bridges with tall, slender towers are structurally more efficient than those with short, squat towers. The steeper cable angles reduce the compression demand on the deck, allowing a lighter deck structure for the same span length. The installation of each stay cable is not a simple attachment operation. Each cable is fabricated to a specific length calculated from the geometric survey of the tower and deck positions at the time of installation, accounting for the elastic shortening of the cable under its design tension, the temperature at time of installation, and the deflection of the tower and deck under the loads present at that construction stage. After installation, the cable is stressed to a target initial tension using hydraulic jacks at the deck anchorage, and the resulting geometry of the deck, its elevation and alignment relative to the design profile, is surveyed. If the measured geometry deviates from the model prediction beyond acceptable tolerance, the cable tension is adjusted. This iterative process of install, stress, survey, and adjust continues for every cable on every segment, and the accumulated history of all previous adjustments must be maintained and incorporated into the prediction for the next segment. A cable-stayed bridge under construction is a continuously updated structural model, and the construction engineer's role is to manage the gap. The tower itself undergoes significant deformation during the balanced cantilever construction process. As deck segments are added and cable tensions are applied, the tower deflects under the combined action of cable forces from both sides, which ideally cancel to produce zero net horizontal force, but in practice produce small forces due to wind and temperature effects. The construction control model must track tower deflections in 3 dimensions: longitudinal, transverse, and rotational. On long-span bridges in windy environments, the transverse deflection of the tower requires real-time wind monitoring. Cable-stayed bridges using the balanced cantilever method are now the standard approach for main spans exceeding 300 meters globally. The Millau Viaduct in France, the Sutong Bridge in China, and the Arthur Ravenel Jr. Bridge were all constructed using this method. Whether using precast concrete, steel box girders, or cast-in-place concrete, the fundamental sequence remains consistent. The method has been refined so that construction tolerances of 10 to 20 millimeters are routinely achieved on spans of several hundred meters, a precision that requires the integration of structural analysis, surveying, testing, and monitoring into a single coordinated operation. The construction method has well-defined limits and failure modes that define the boundaries of what is achievable. The maximum imbalance between the 2 cantilever arms at any construction stage is limited by the tower's bending capacity at its base. Exceeding this limit requires either slowing the construction on the leading arm, accelerating the lagging arm, or providing temporary supports. Cable fatigue during construction, from the daily thermal cycling of cable tension as temperature changes move the deck and tower, accumulates damage. This damage occurs at the anchor locations before the bridge even opens to traffic and must be accounted for in the design fatigue life. The deck closure at midspan requires precise control of the relative elevation and alignment of the 2 cantilever tips. Any mismatch at closure is locked into the completed structure as a permanent geometric imperfection that affects the distribution of live load. On long spans subject to different thermal conditions, achieving required closure tolerance requires careful timing relative to the time of day. So how is a cable-stayed bridge main tower built? And why does the deck construction begin before the tower is finished? It is a self-equilibrating system in which cables, deck, and tower must be built simultaneously in a sequence that maintains structural equilibrium. The balanced cantilever method achieves this by extending the deck outward from the tower in both directions simultaneously. Each new segment connects to a cable anchored progressively higher on the rising tower, maintaining the balance of forces at the base. Tower and deck rise together, each making the other's existence structurally possible at every stage of construction. The finished bridge is the end state of a construction process that was itself a structural system at every intermediate stage. It is equally dependent on the integration of geometry, force, and material behavior that defines cable-stayed bridge engineering. What happens when a stay cable on a completed bridge develops corrosion or fatigue damage and must be replaced while the bridge remains open? The cable replacement sequence is a structural operation that requires the same level of construction control engineering as the original erection. I have covered that engineering sequence in another video. Join me there to explore how we maintain these massive structures.